Okay, hi, AP Calc AB kids. So we are working on Chapter 4, Practice Exam Part 2, and for the Chapter 4, Part 2 exam. And so we are getting through here. We are on problem number 4. So in problem number 4, a rectangular tank that is 108 feet cubed. The minute I read that, I'm thinking, that's volume. So that's volume. The units say is volume, and it's a rectangular tank. It's got a square base and an open top. Okay, so it's to be constructed of a sheet steel of given thickness. Find the dimension of the tank with minimum weight. So now you're going to have a minimum weight when you have the least amount of surface area that you're going to cover because it's got a given thickness. So that minimum weight is going to translate to how much stuff you're going to use to make this box that has a volume of 108 cubic feet. Okay, so before I go any further, I usually say, okay, it has a square base. That's what the box is going to look like. And I state the dimensions are going to be x by x by h. So then I know my volume is going to be 108 x squared h. And then remember, we do this kind of a system of equation kind of thing, where we have this equation. Well, we have the first equation, the volume equation, and that's going to have two variables in it, as well, and the same variables exist in the surface area. Now we want to maximize surface area in here. In this case, we want to have a minimum surface area, so we have a minimum weight. Okay, so with that, I'm going to take this expression for h, and then I'm going to plug it in. I'm going to plug that in to h in the surface area equation to get a surface area that's just in one variable, right? Not two variables. So here you go. Here it is right there. That'll be our surface area then, our surface area equation. And then remember, what we want to do next is we want to take the derivative of the surface area. So when we do, we just get 2x minus 432 over x squared. We're looking for critical numbers, right? So the critical numbers are going to be, when we set that equal to 0, we're going to get x is equal to 6 for a critical number. Okay, so now if you wanted to clinch it, which I usually do, you have the second derivative is equal to 2 plus 864x to the negative 3. That's always going to be greater than 0. Always going to be greater than 0. So s double prime of 6 is greater than 0 also, which means that your graph is concave up, and 6, that's supposed to be an s for the surface area, is going to be at a minimum value. Okay, and that's what we want. We want that. So then we just have to go back and plug h in. I thought I did up here. Go plug h back in so that you can get your value for the height when the base, when the base is going to be 6 by 6, your height is then going to be 3. Okay, so there you have it. There it is. There you go. And that problem's done. Okay, 6 by 6 by 3 feet is what that's going to look like. Okay, for the next one, a child flies a kite of 90 feet. Flies a kite at a height of 90 feet. The wind carrying the kite horizontally away from the child at a rate of 30 feet per second. How fast must the child let the string out when the kite is 150 feet away from the child? So this, I'm big on drawing whatever it is that you're looking at. So here's the kite, right? It's got that string. It's attaching to the string right here. Your string is the 150 feet that come back to the child's hand, right? So we know that it's flying at a constant height of 90 feet. Kind of unrealistic, but that's what we're doing. And then it's moving out. The x value is the horizontal distance. It says that the child flies a kite at a height of 90 feet. We got that covered. Here's the 90 feet. And I have some variables on there. I'll get to those in a second. The wind carrying the kite horizontally away from the child at a rate of 30 feet per second. We have that down here. You can see that that's going to make x get bigger, meaning that the dx dt, the rate at which x is changing, is going to be positive. How fast must the child let the string out when the kite is 150 feet away from the child? So here's the child right here, the C child, the CH child. All right, down here, so that the kite is 150 feet away. Okay, so we want to know how much bigger is Z, or how much faster is Z going to go out. So we are looking for dZdt here. Okay, now I'm going to move down to the bottom right so you can see what I did here. So this is a Pythagorean. Can you see I have the variables on here, X, Y, and Z? So it's a Pythagorean problem. Let me make this bigger so that's what you're seeing here. So I'm going to okay, so we're trying to find dZdt here. So I'm just going to box that off so I'm kind of localized there. Okay, so I have x squared plus y squared is equal to z squared. Then you see you get this second line when you take the derivative with respect to t. 2x dx dt plus 2y dy dt is equal to 2z dz dt. Now, if you notice, when we put in, we don't know what x is yet. So what we're going to have to do is look at this. We're going to have to find what x is. So x turns out to be 20 using the Pythagorean theorem. X is equal to the square root of 150 squared minus 90 squared, which is the square root of 14,400. And we get x is equal to 120. We're going to need that. Now you plug that in, and we know that dx dt is 30. Right? So now we have 2 times 120 times 30 plus. That second term is going to turn out to be 2 times 90 times 0 because dy dt is equal to 0. So that goes to 0. And then the right-hand side of the equation, 2 times 150, dz dt is what you're looking for. Okay, so then in the next line, you've got, it turns out 2 times 120 times 30 is going to be 7,200, and that's equal to 300 dz dt. Divide by 300, and you get this. You get your answer. 24 dz dt is 24 feet per second. That's the rate at which the string has to leave the child's hand. Okay, so that's the answer to that. So a rate of, what do we say, 24 feet per second. All right. The next one is a cone problem. I really like this problem. And so you're going to use similar triangles in this one. So over the weekend, if you are struggling with these at all you have to do is Google cone-related rate problems. There are tons of them on Khan Academy, and there's just tons of them everywhere. Math is Fun. I think they have a couple on Math is Fun. Mathisfun.com. All right, so it says the water is flowing at the rate of 60 meters cubed. I know that, per minute, I'm sorry. So that's a dVdt. When I read that, it's just the volume changing over time. From a shallow concrete conical reservoir, vertex down, of base radius 40 meters and height 8 meters. Now, my drawing is not going to look accurate, but that's okay. So I go ahead and draw it, right? And don't pay attention to anything below this line. So I draw it and I think, okay, water's flowing at the rate of 60 meters cubed from a shallow concrete conical reservoir, vertex down. Okay, so it's flowing from. Okay. So now what we want to know is how fast, the first question, is the water level falling when the water is 6 meters deep? Okay. So there's one thing that I've got to check on here. I know that the water is flowing from, so I've got a 60 in here. I just got to check. I'm going to make a comment about that, but if you saw it, you were checking your work, we'll be fixing that in a second. So here's my diagram. I've got the radius is going to be 40 meters, right? Let me double check that again. 40 meters. Boop, radius is, base radius 40 meters, right? And the height is 8 meters. So I kind of mark that. That is the radius of the cone and the height of the cone. And then if you look, water is inside of this. There's a radius and a height. Those are the quantities that are going to change. The cone is always going to be 40 meters for the radius, and the height's always going to be 8 meters. So it's the place where the water is that's going to have the change occurring, okay? So here's what we do. we know we have a volume equation for cones, right? And that's right here. We start off with that equation. We're always with related rates, we're starting with an equation. And now, I don't know anything about the radius, really. Except that I don't know, I'm not being asked about dRdt, and I'm being asked about dHdt. So what we do is we substitute, and I'll show you how I get that. We want everything to go to h's, and here's how we do this. We don't have any dRdt information here. So this is a kind of a nice setup here. So here's the cone. You have two similar triangles in the cone. One is involving the whole cone, and one is involving just the water that's in there, or whatever fluid is in there. It looks kind of green. All right, so if you look what I have down below here, I can set up a ratio with similar triangles that I know that the radius of the water over the height of the water is equal to the radius of the cone ratio over the height of the cone. So it turns out that here, R over H, now you're talking on the left-hand side, that's the actual changing quantities. R over H is always going to equal 40 over 8 then. So I can say that R is equal to 5H. So that's the quantity we're going to substitute into our formula equation. And we're going to go back here. So here's my work. So you can see here's my new volume equation here. I plug in 5H. R is equal to 5H instead of having an R and an H in the equation. And then we multiply and we get the volume is equal to 25 pi over 3 H cubed. That is an easy function to be able, or equation to take the derivative implicitly with. Remember, we're taking ddt of both sides of the equation. So we end up with the derivative, dv dt is equal to 25 pi over 3 times the derivative, remember, of this h cubed, which was 3h squared. I cancel the 3's, and then I tack on the dh dt for implicit differentiation. So you end up with this line, dv dt is equal to 25 pi h squared dh dt. And see, you're looking for dh dt, but I'm just going to plug everything in that I have. Now, the water is flowing out, right? So there's one thing that I left out on here, and it's kind of a serious issue here. It makes the dv dt negative. It means that your volume is decreasing. So the rate dv dt is negative. So I'm going to put the negative on there. So that's going to make our end result dh dt is negative. I'm going to put the negative here. Okay. So we solve dh dt and we eventually get this, where we have it's negative 0.0212 meters per second. But that's not what it asks for. It asks for in centimeters per second. So your answer, you move your decimal place over twice, and you get 2.12 centimeters per second. Okay, and that's the answer for your first one. Now, then the radius of the water surface is changing then at. So I have to figure that out now. So come down here. Since R is equal to 5H there, you already know what dH dt. Here's your dH dt, right? And then we again wrote that here in centimeters per second. And this is negative, by the way. And I put negative there. It's negative, but it just says the water level is falling, so we leave it as a positive there. So coming back down over here, R is equal to H. So taking the derivative, I'm going to get a little blue here, the derivative with respect to time of both sides of this equation, we get this. dr dt is equal to 5 dh dt. We just take 2.12 centimeters per second, even though it's negative. Here, that's negative, that's negative. So we get negative 10.61 centimeters per second. That is the end of the second question here then. In that the radius of the water's surface is changing at 10.61 centimeters per minute. I think I might have said seconds there. Let me fix that. Oh, geez, if I erase this, it's going to blow away. Here I have, it's in minutes here. Let me change the seconds here. All right, so there we have it. There it is. There you go. Okay. All right. So one more problem to do. This one is just like taking derivatives, but splitting up the differentials is all that we're doing. For the following equation, A, find dy, and evaluate taking derivatives, but splitting up the differentials. So we're focusing right here in the middle is where the work is. Try to ignore my writing there for a little bit. So with this, we're going to go right down and look at this area. So dy dx is 3x squared. Oh, I'm sorry. Given y is equal to x cubed minus 3x, x is equal to 5, and dx is equal to 0.01. We want to find dy, and we want to evaluate dy for the given value of x and dx. What dy is a change in y. Dx is a change in x. So once we find dy dx, we multiply both sides by dx. So we get this dy is equal to 3x squared minus 3 dx. And once we do that, then we're going to take dy, we're going to evaluate it for x. X is equal to 5. And let me erase this here. X is equal to 5 and dx is equal to 0.01. We plug in, and it turns out that we get 0.72. Okay? So now what this is really about is that, so a very, very small change in delta x, a very small change in delta x can often cause a larger change in y, okay? Then that would be dy in dy, or whatever quantities that you're talking about. But think of engineering, how a small change in one measurement can be absolutely disastrous. Okay, and so you think about things like the Space Shuttle Challenger when the measurements were off. And so things like that can often have, where you have even just a small error in x, 0.01, it turns out that it affects dy, 0.72. So there's quite a bit of sensitivity there in changing the change in y, or how the change in y is so much more affected than the change in x. So anyway, you have your answers for your solutions here. And if you have any questions, you by all means can email me. I'll be sending you this copy as well, and the videos. All right, so have a great weekend and have a great day tomorrow. I will see you when I see you.